Welcome to my channel. Today, we're going to discuss one of the most fascinating phenomena in modern AI, in-context learning. Here's something that might surprise you. Traditional machine learning requires you to update a model's weights through backpropagation over many iterations, but transformers can do something remarkable. They can learn new tasks just by reading a few examples in their input, without any weight updates at all. On the left, you see traditional training that requires collecting data, updating weights through gradient descent, and iterating many times. This approach is crossed out because in-context learning bypasses all of that. On the right, you see how in-context learning works. You simply provide examples like happy maps to positive, sad maps to negative, and then ask about the word great. The transformer processes these examples and outputs the correct answer, positive. How does this work? That's exactly what we'll explore in this video. So, what exactly is in-context learning? Let's define it precisely. In-context learning is the ability of a pre-trained model to adapt to new tasks based on examples or instructions provided in the input context without modifying model parameters. Notice the key phrases here: adapt to new tasks and without modifying parameters. This is fundamentally different from how we traditionally think about machine learning. There are three essential properties that make in-context learning special. First, no weight updates are needed. The model's parameters stay completely frozen during inference. Second, you only need a few examples. Typically, just 2 to 5 demonstrations are enough to teach the model a new task. Third, it's task agnostic. The same model can handle translation, sentiment analysis, coding, and much more just by changing the examples in the prompt. Let's see this in action with sentiment classification. We provide examples: I love this movie, maps to positive. This was terrible, maps to negative. Amazing experience, maps to positive. And waste of time, maps to negative. Now, when we present a new input like great product, the model correctly outputs positive. It learned the task without any training. Now let's break down the anatomy of an in-context learning prompt. Every ICL prompt has 3 essential components. First is the task instruction. This tells the model what you want it to do. In our example, we have translate the following English phrases to French. This sets the context and the expected behavior. Second, we have the demonstrations. These are the input-output pairs that teach the model the pattern. Here, we show hello maps to bonjour, thank you maps to merci, and goodbye maps to au revoir. Each demonstration reinforces the translation pattern. The model learns not from explicit rules, but from the examples themselves. Third is the query. This is the new input you want the model to process. We ask English, good morning, and leave a blank for the French output. The model now has everything it needs to complete this task. Notice the consistent pattern throughout. Input maps to output. This structure is crucial. The model recognizes this pattern from the demonstrations and applies it to the query. Any deviation from this format can confuse the model and lead to incorrect results. The discovery of in-context learning came with a landmark moment in AI history. Let's look at the evolution of GPT models. GPT-1 was released in 2018 with 117 million parameters. It showed that language models could be pre-trained and fine-tuned for various tasks. GPT-2 came in 2019 with 1.5 billion parameters. It demonstrated impressive text generation but still relied heavily on fine-tuning for specific tasks. Then came GPT-3 in 2020 with a massive 175 billion parameters. This is where everything changed. At this scale, something remarkable happened. The model developed the ability to perform tasks it was never explicitly trained for. Translation, arithmetic, coding, reasoning, all became possible just by providing examples in the prompt. This is what researchers call emergence at scale. As you increase the model size, new capabilities appear that weren't present in smaller models. The paper that announced this was titled "Language Models Are Few-Shot Learners," and that title captured the essence of the discovery. These models don't need thousands of training examples. They can learn from just a few demonstrations. This was the breakthrough that unlocked in-context learning as we know it today. Now let's understand the mechanism that enables in-context learning, the attention mechanism. Think of attention as a spotlight that searches through the context to find relevant information. Here's how it works in practice. We have a sequence of tokens. Happy maps to positive, sad maps to negative, great maps to positive, and then our query, amazing, maps to question mark. When the model needs to predict what comes after amazing, it uses attention to look back at all the previous tokens. The attention weights show where the model is looking. Notice how the lines connecting amazing to other tokens have different thicknesses. The thicker lines indicate stronger attention. The model attends most strongly to the word great and its output positive because great is semantically similar to amazing. It also pays attention to happy and positive for the same reason. The flow is straightforward. The query attends to similar inputs in the demonstrations, copies the pattern from their outputs, and generates the correct answer. This is pattern matching at work. The model finds semantically similar examples and copies the associated output pattern to the new query. It's essentially using attention to transfer information from examples to the answer. Let's dive deeper into a specific attention pattern called induction heads. These are the true workhorses of in-context learning. Here's the core idea. Imagine you see the sequence A, B, A, question mark. An induction head recognizes a simple pattern. I've seen A before and it was followed by B, so when I see A again, I should predict B. This is the copy-paste mechanism of in-context learning. The induction head performs two steps. First, it searches backwards to find a previous occurrence of the same token or a similar pattern. Second, it copies whatever token came after that previous occurrence. Let's see this with a real example. Consider the analogy Paris is to France as Berlin is to blank. The induction head recognizes the pattern. A capital city is followed by its country. It finds Paris followed by France, then applies the same pattern to Berlin, predicting Germany. This is remarkably simple yet incredibly powerful. The model doesn't need to understand geography explicitly. It just needs to recognize and copy patterns from the examples. Research has shown that these induction heads emerge during training and are crucial for in-context learning. Without them, models struggle to learn from contextual examples. Here's a fascinating theoretical insight. Some researchers believe that in-context learning is actually implementing something similar to gradient descent, but hidden within the forward pass. Let's compare the two approaches. In traditional training, you use the weight update rule. Theta equals theta minus eta times the gradients of the loss. This happens over many iterations. You compute the loss on your data, calculate gradients through backpropagation, and update the model weights. In-context learning uses the attention mechanism, attention of Q, K, V. But here's the surprising connection. When you look at the mathematics, the attention operation has a similar structure to gradient updates. The attention layers may be performing implicit optimization as they process the examples. The steps look similar in effect. Traditional training reads data and updates weights. In-context learning reads examples in context and uses attention to implicitly adapt. Both are producing similar effects but through different mechanisms. The key insight here is that many training steps might be equivalent to a single forward pass in a large transformer. The model learns during pre-training how to perform this implicit optimization. It's essentially solving a learning problem within the inference step itself. Forward pass equals learning. That's the profound implication of this theory. This brings us to an even more intriguing concept, Mesa-Optimization. Think of it as a machine that learned to build learning machines. Here's the structure. During pre-training, which you can think of as the outer loop, the model is trained on massive amounts of data. Books, websites, code, articles, everything flows through the model as it learns to predict the next token. But something deeper happens during this process. The model doesn't just learn facts or patterns, it learns how to learn. An inner loop emerges within the model itself. The model develops internal circuits that can adapt to new tasks from examples. This is the ICL algorithm that emerges from pre-training. You can visualize this as a mini optimizer living inside the transformer. When you provide few-shot examples at inference time, this internal learning algorithm kicks in. It's as if the transformer contains a small neural network that can rapidly adapt based on the demonstrations you provide. This is meta-learning at its finest. The model learned to learn during pre-training, and now it can apply this capability to any task you present. The emergent circuits for learning to learn, meta-learning adaptation, and task flexibility all arise from this Mesa-Optimization process. It's a profound idea. The pre-training created a general-purpose learning algorithm inside the model. Let's explore how models internally represent the tasks they learn in context. The key concept here is task vectors. When you provide examples like happy maps to positive, sad maps to negative, and great maps to positive, the model processes these and creates internal representations. Imagine a high-dimensional representation space. Each example gets embedded as a point in this space. As the model processes multiple examples of the same task, these points cluster together. From this cluster, a task vector emerges. This vector encodes the essence of the task. You can think of it as a direction in the representation space that says, move from input to output in this way. When a new query comes in, the model combines it with this task vector. The formula is essentially output equals input plus task vector. Different tasks create different vectors in this space. Sentiment analysis has its vector, translation has another, question answering has yet another. The model learns to construct these task-specific vectors from just a few examples. This is why in-context learning is so flexible. The same model can handle completely different tasks because it can construct new task vectors on the fly based on whatever examples you provide. The task representation is emergent and dynamic. Now, it's important to understand when in-context learning fails. It's not a magic solution for everything. First, there's order sensitivity. The sequence of your examples matters. If you provide examples A to 1, B to 2, C to 3 in that order, you might get correct results. But shuffle them to C to 3, A to 1, B to 2, and the model might give completely different, incorrect outputs. The same information, different order, different results. Second, format sensitivity. How you structure your prompt is crucial. Input X, arrow, output Y might work perfectly, while X equals Y with the same content might fail completely. The model is sensitive to these formatting details because it learned specific patterns during pre-training. Third, context length limitations. The model can only see a limited window of text. If you need more examples than fit in the context window, earlier examples get pushed out and lost. The model simply cannot access information outside its viewing frame. Fourth, reasoning limits. In-context learning excels at pattern matching, but struggles with tasks requiring genuine multi-step reasoning. If the task requires novel logical inference that can't be reduced to pattern copying, ICL may fall short. The key takeaways? Prompt engineering matters significantly. Not all tasks are suitable for ICL, and fine-tuning may be necessary for complex or high-stakes applications. Let's compare in-context learning with the traditional approach of fine-tuning. When should you use each? In-context learning shines in several areas. Setup speed is instant. You just write a prompt and go. Data requirements are minimal. Just 2 to 10 examples typically suffice. And flexibility is very high because you can switch tasks just by changing the prompt. On the other hand, fine-tuning has its own strengths. Peak performance can reach excellent levels when you have enough data, but setup takes hours or even days of training. You need hundreds or thousands of examples for good results, and the model becomes task-specific, losing the flexibility to easily switch between tasks. Here's a simple decision flow chart. Do you need quick results with limited data? If yes, use in-context learning. It's faster, more flexible, and requires minimal investment. If no, meaning you have time, data, and need maximum performance for a specific task, then fine-tuning is the better choice. The investment is larger, but the returns can be higher. The best practice that many practitioners follow is to start with in-context learning for rapid prototyping and validation. If you find that ICL performance isn't sufficient for your production needs, then invest in fine-tuning. This approach minimizes risk and gets you results faster.
Let's summarize what we've learned about in-context learning. We discovered that models can learn without weight updates, simply by reading examples in their context. This works through attention mechanisms that copy patterns from demonstrations. Induction heads serve as the pattern matchers that make this possible. The process may be equivalent to implicit gradient descent happening within the forward pass, and Mesa-Optimization Theory suggests that transformers learn to implement learning algorithms during pre-training. Today, in-context learning powers many applications we use daily. Chatbots, code assistants, writing tools, and research applications all leverage this capability. Looking to the future, we're seeing context windows grow to millions of tokens, enabling even more examples and richer context. Reasoning capabilities are improving, allowing models to handle more complex multi-step tasks. And there are still open questions about how deep this learning really goes and what its fundamental limits are. We're just beginning to understand the full potential of in-context learning. If you found this video helpful, please like and subscribe to the channel for more AI engineering content. Thanks for watching.